We're back. Apologies for the interruption. I had to change venues. So we're talking about radiosondes. These provide measurements of atmospheric pressure, temperature, humidity, wind speed and direction from the Earth's surface up to an altitude of about 30 kilometers. That's well and truly into the stratosphere. This one here that I'm holding weighs less than your mobile phone. It has a thermistor measuring atmospheric temperature, a barometer which measures pressure, a hygrometer which measures moisture in the air through relative humidity, and GPS receiver, radio transmitter and a battery. But this is a typical radiosonde. It's attached to these helium or hydrogen-filled balloons, weather balloons, launched from various locations around the world multiple times a day. In Australia, there's maybe, 20 or so radiosonde launch sites, typically co-located with airports. These are part of a global network of radiosonde launch sites, and they provide the physical state of the atmosphere for all these locations multiple times a day, at least twice a day. And these measurements form the backbone of all weather forecasts. Here's an example of the radiosonde measured atmospheric pressure. It's from a radiosonde launched on 9 AM Christmas Day last year from Perth Airport. Now, we can see Perth Airport is located about 20 metres above sea level. And the radiosonde measures pressure from the launch elevation right up to about just over 30 kilometres into the atmosphere. So it's a nice smooth decrease with altitude as we expect, and kind of like an exponential decay. And I say kind of like an exponential function because if we fit an exponential model to the pressure variation with altitude, it fits well in some places, but not so well in other places. So here we have pressure at a given altitude, Z, is almost equal to the mean sea level pressure times the exponential of the minus altitude divided by an H bar parameter. We'll explain what these two parameters, P mean sea level and H bar mean in a tick. But you can see that because this particular solid line, this model, was fit to the observations in the lower part of the profile. It fits quite well to the lower part, up to about 10 kilometres. But then at about 15 kilometres or 20 kilometres, that fit doesn't fit so well. So nevertheless, we fit the model by taking the first two observations in the profile at those two altitudes, Z2 and Z1, and divide that by the natural logarithm of the pressures at those respective altitudes to give us our scale height. Mean sea level pressure is obtained by taking the estimates of scale height, one of the altitudes of interest, and just rearranging this equation to give us that. So in this case, we've estimated for 9 AM, 25th of December 2019, the scale height is 8.07 kilometres, and the mean sea level pressure is 1,014.5 hectopascals. Temperature, as we expect, will decrease with altitude for the troposphere. So here we have, in this case, we've got temperature on the x-axis and altitude on the y-axis. And we can see generally up until about the 15 kilometre mark, you're getting a general decrease in temperature from the Earth's surface right up to about 15 kilometres. Then there's the tropopause, and then you start getting to the stratosphere and there's an increase in temperature. The rate of decrease of temperature is with altitude is called the lapse rate. In this case, for that first 10 or so kilometres of the atmosphere, the lapse rate is estimated to be 6.5 degrees Celsius per kilometre. So uh, with every 1 kilometer increase in altitude, the temperature of the air drops by 6.5 kilometers. And talk about this idea of generally decreasing. So we talk about that general behavior over the whole troposphere, but we can see here in this radiosonde observations, we see that decrease initially from the surface up to about 200 or 300 meters. But then we start to see an increase in temperature. And then around about 1 kilometer mark, that decrease in temperature again. So when temperature starts to exhibit this behavior that's contrary to what we expect, namely we see an increase in temperature with altitude rather than an expected decrease in temperature, that's called a temperature inversion. And so, as I said, it's the trend in the opposite direction to what we generally expect. The question might be, when does that happen? When do we see an increase in temperature with increase in elevation? And here's an example of those times we see it. In this case, and we'll go into some of the concepts that lead to this formation later on in this lecture. But here we have cold air sinking into the valleys between two hills. And cold air is denser and it will slide underneath warmer air. Remember, more dense things will sink below less dense things. So the air above this cold layer is warmer, less dense, therefore more buoyant. And another thing we'll learn later on is that colder air doesn't hold as much moisture as warm air. So as the air sliding down the valley starts to cool, it loses that water vapor. It becomes condensed and forms clouds. And so we have a cold layer underneath a warm layer. So here's an example in a temperature inversion where temperature will increase with altitude. Let's think about the behavior or the relationship between pressure and temperature for a bit. So here we have a parcel of air, a volume of air with atmospheric pressure exerting force in all directions on that parcel. Molecules inside that parcel of air will carry along their merry way on what's called their mean free path. That's the distance between collisions of the molecules. As we increase the pressure on that volume of air, the mean free path reduces. That means the distance or the time between collisions decreases, so they collide more often. The collision between molecules increases the energy inside that volume, which results in an increase in temperature of that volume. The increase in pressure also results in a decrease in volume, and the decrease in volume and the mass staying the same means the density has increased. We'll cover this a bit later on too. But the opposite also works here. So if we consider a decrease in atmospheric pressure, that means the molecules have more space to move around before they collide into each other. Energy decreases, so the temperature decreases, volume of the gas increases, the gas expands, and the density decreases. The relationship between pressure, the volume, and the temperature is expressed in the ideal gas laws, also known as the equation of state. Here we have the pressure of a gas multiplied by its volume is equal to and I'll have to pause here because